Hi, I am Nirmala Devi, serving as Assistant Professor in the Department of Biochemistry, Biotechnology and Bioinformatics, Davinashalingam Institute for Home Science and Higher Education for Women, Coimbatore. You have chosen to do the lesson on production of high fructose corn syrup. Sweeteners are necessary to impart sweetness to food products. An ideal sweetener is as sweet as or sweeter than sucrose, which has a pleasant taste, colorless, odorless, readily soluble, stable, functional and economically feasible. It is also non-toxic, does not promote dental caries and is either metabolized normally or excreted from the body unchanged without contributing to any metabolic abnormalities. The most common examples of natural sweeteners are sucrose, liquid glucose and invert syrup. Corn syrup is one of several natural sweeteners derived from cornstarch. It is used in a wide variety of food products including cookies, crackers, ketchup, cereals, flavored yogurts, ice cream, preserved meats, canned fruits and vegetables, soups, beers and many other food products. One derivative of corn syrup is high fructose corn syrup, which is as sweet as sugar and is often used in soft drink industries. The term corn sweetener has been the generic term for a wide variety of nutritive carbohydrates prepared by the hydrolysis of cornstarch. These products are differentiated principally by the degree of hydrolysis. The functional properties of a corn sweetener are a consequence of the particular type and mixture of hydrolytic products. Functional properties include sweetness, fermentability, viscosity, flavor enhancement, osmotic pressure, humectancy, hygroscopicity, color development, cohesiveness, nutritional quality and texture enhancement and crystallization prevention. Introduction. Glucose has almost 65% of the sweetness of sucrose on a weight basis. Fructose has 120 to 180% depending on the conditions of testing. Thus, a means of converting glucose to fructose increases its sweetness because glucose is available readily and becomes very cheap when cornstarch is abundant. Alkaline isomerization is possible but produces excessive color and side products. As you all know, glucose is an isomer of fructose. Let us see the different types of sweeteners. Sweeteners are categorized based on relative sweetness of different sweeteners to sucrose as shown here. Caloric sweeteners, low caloric sweeteners, non-caloric synthetic sweeteners and non-caloric natural sweeteners. Let us see the history and development of corn sweeteners now. The process for converting starches into sugars was first developed in Japan in the 800s using arrowroot. In 1811, the Russian chemist Kirchhoff rediscovered this process when he heated potato starch in a weak solution of sulfuric acid to produce several starch-derived sweeteners including dextrose. In the United States, this acid conversion method was adapted to cornstarch. In 1935, only one type of corn syrup was available, that is 42DE, that is dextrose equivalent acid converted corn syrup. Although this product was useful in many applications, it lacked the sweetness of sucrose and could not compete as a sweetener. When corn syrup was acid converted to higher degrees of hydrolysis, the resulting products were often highly discolored and contained bitter byproducts from the acid mediated reaction. In the early 1960s, significant quantities of crystalline dextrose were being produced using enzymes. This process remained the principal source of corn syrup until the year 1967, when the enzyme conversion method for producing high fructose corn syrup was commercialized. At first, this was a batch process requiring several days. In 1972, a continuous enzyme conversion process was developed that reduced the time to several minutes or hours. The commercial development of glucose isomerase, the most predominant enzyme used in fermentation technology, which converts glucose to its sweetener isomer, fructose, was a major milestone event in the corn sweetener industry in 1977 by Casey. The first high fructose corn syrup, commonly referred to as HFCS, contained 15% fructose. The manufacturing process known as isomerization originally involved the direct addition of an isomerase enzyme to a dextrose substrate in a batch reactor. Further, process improvements resulted in HFCS products containing 42% and 55% fructose. The hydrolysis products of starch can be classified conveniently on the basis of the reducing sugars they contain. Since starch is a homopolymer of anhydroglucose, its depolymerization through hydrolysis results in a mixture of glucose oligomers ranging typically from the monomer glucose to glucose multiples containing many units of glucose linked together. The reducing sugars contained in these mixtures can be assayed and expressed as they relate to the reducing power of dextrose in terms of a dextrose equivalent. The higher the degree of hydrolysis, the greater the DE value, that is dextrose equivalent value, and the corn sweeteners are categorized based on their dextrose equivalent values. Let us see the production of high fructose corn syrup now. The key step in the entire process of production of high fructose corn syrup is the enzymatic isomerization utilizing immobilized glucose isomerase enzyme. The economic and technical success of the isomerization reaction depends upon the enzymes that catalyze the ultimate conversion of the starch polymer to dextrose monomer. This flowchart outlines the production of high fructose corn syrup. The process may be divided into 18 separate steps in 5 principal areas of operation. These 5 areas include dextrose production, primary refining and chemical treatment to produce dextrose feedstock, isomerization of dextrose to produce 42% fructose, secondary refining of 42% fructose, and finally fractionation of 42% fructose for 55% fructose. The first stage in high fructose corn syrup production is the hydrolysis of polymeric starch to monomeric glucose, and this process is measured by a dextrose equivalent in which the specific chemical reducing power of the mixture of monomer, oligomers and polymers is measured relative to that of pure glucose or dextrose. The latter is deemed to have a DE value of 100. As glycosidic bonds are hydrolyzed and reducing aldehyde groups are exposed, the DE value rises from almost 0 for starch to its final value. In commercial practice, hydrolysis is stopped at 42 DE and 63 DE to give products which have those combinations of osmolarity, sweetness and hygroscopicity which are suitable for a range of commercial applications. In the later stages of high fructose corn syrup production, large-scale chromatographic techniques are used to produce syrups with various proportions of fructose and glucose. The degree of isomerization or DI is the percentage of sugars, dry bases by weight as fructose. Thus, a 42 DI or regular high fructose corn syrup contains 42% fructose, 52% glucose and 6% of higher sugars or saccharides. Now let us see the properties of high fructose corn syrup. The commonly accepted term HFCS is sometimes replaced by HFGS, that is high fructose glucose syrup or isoglucose. The expression of ultra high fructose corn syrup is restricted to those syrups having a DE value greater than 50. It is a common practice to incorporate the degree of isomerization value in the product description. For example, HFCS 42, HFCS 55 and HFCS 90, which are shown here, indicates that HFCS 42 contains 42% fructose and 52% glucose, whereas HFCS 55 contains 55% fructose and 41% glucose, and HFCS 90 contains 90% fructose and 8% glucose. Predominant enzyme used in the production of HFCS is glucose isomerase. Immobilized glucose isomerase is used to convert a refined 93 to 96% dextrose hydrolysate to a 42% fructose product. Commercial enzymes are produced intracellularly from a variety of bacterial sources. Selected commercial enzyme products and recommended operating conditions are listed and are shown here. During the initial stages of high fructose corn syrup development in the early 1960s, it becomes obvious that the use of a soluble isomerase for fructose production would require a high enzyme dose or a long reaction time. The high dose was economically unacceptable, and the prolonged reaction time caused the formation of undesirable byproducts such as mannose, psychose, color and off flavors that increased refining costs. Consequently, efforts were directed to the development of immobilized enzyme systems that would improve process economics. An immobilized isomerase system was found to have many of the benefits and few of the disadvantages of bound enzyme systems proposed for other purposes. For instance, the substrate used for high fructose corn syrup production is a clarified and refined low viscosity stream that is passed easily through a column of bound enzyme. Both the substrate, that is dextrose, and the product, that is the fructose, which is formed as an end product, are simple low molecular weight saccharides that easily diffuse through porous carriers used for enzyme immobilization. In addition, the bound enzyme exhibits very long half-lives of several months under normal process conditions, resulting in low enzyme cost. Also, reaction time due to the high enzyme concentration is reduced sufficiently in continuous operation to minimize production of byproducts. Consequently, with the exception of initial fructose production in the late 1960s, all HFCS has been manufactured using immobilized enzyme. Glucose isomerase is well suited to use in an immobilized form since it is intracellular, stable at elevated temperatures, sufficient to discourage microbial contamination, and because all the reactants are small molecules, so that there are very few diffusional problems associated with this technology. Two isomerase immobilization processes are in use to produce commercial products. These are referred to as whole cell and soluble enzyme processes. In the whole cell process, the bacterial cells containing the intracellular enzyme isomerase are recovered from fermentation broth and treated to immobilize the enzyme within the cells. In a commercial process, bacterial cells are concentrated by centrifugation, disrupted by homogenation, cross-linked with glutaraldehyde and flocculate with a cationic flocculant. The resulting material is filtered, extruded, dried and sieved to produce a 300 to 1000 micromolar final product. In another process, a cell gelatin mixture is cross-linked with glutaraldehyde, washed and sealed. Cellular immobilized enzyme products are discarded after use and replaced with new material. In the soluble enzyme process, cells are treated enzymatically or by physical means to break the cell wall and release isomerase enzymes. The isomerase is recovered by filtration or centrifugation and concentrated by ultrafiltration. The soluble enzyme is then bound to a carrier. One method involves recovering a purified soluble isomerase enzyme by ultrafiltration and crystallization and contacting the enzyme for about 3 to 5 hours with a carrier composed of DEAE cellulose, titanium dioxide and polystyrene. The material is ground to produce a 400 to 800 micrometer final product. In another type of immobilization, polyamine is absorbed on alumina and treated with glutaraldehyde to cross-link the amine and immobilize the isomerase by forming covalent bonds between the enzyme amino groups and the carrier aldehyde groups. In some cases, the carrier can be reused for several cycles by removing residual enzyme and rebinding with fresh enzyme. For instance, the DEAE cellulose carrier can be regenerated by washing sequentially with water, 2% sodium hydroxide, water buffer and rinse water to remove inactivated enzyme and accumulated impurities. Fresh isomerase is then bound by batch or column operation to achieve 95% of the original capacity. Alternatively, additional enzyme can be added periodically via the feed and bound to the carrier during the isomerization process to maintain a constant level of activity over a long period of operations. The immobilized isomerase is loaded in a column and substrate is passed through at a rate that produces an effluent containing 42% fructose. Several parameters must be controlled carefully for maximize the productivity. These parameters include feed purity, solids, temperature, pH, oxygen level, magnesium content and reaction time. Let us see all these parameters one by one. Isomerase feed is refined hydrolysate containing 93 to 96% dextrose. Efficient refining is required to remove insoluble material that may accumulate in the column over time and cause pressure drop problems and impurities that could cause inactivation of the enzyme. Ion exchange treatment of feed is required to lower calcium levels to 3 parts per million or less, since the material is inhibitory to isomerase. The next parameter is solid. Feed solid levels is controlled in the 40 to 50% range, generally at about 45%. If the solid level is too high, increased viscosity may reduce rate of feed diffusion within the carrier pores and cause a reduction in the product yield. A solids level that is too low could result in microbial contamination. The next parameter is temperature. Temperature control is important in maximizing productivity and useful life of the column. Normally, temperature is controlled at 55 degrees to 61 degrees centigrade. At a lower temperature, the risk of microbial contamination is increased. As the temperature is increased beyond the recommended range, activity of the isomerase enzyme increases, but at the same time, long-term productivity decreases due to a faster rate of enzyme inactivation. This situation results in a reduction in the useful life of the column. Only when high productivity is required for a short period of time at the expense of long-term productivity is a higher temperature a consideration one. pH. Long-term isomerase stability is highly dependent on pH. Depending on the particular enzyme, recommended pH varies from 7.5 to 8.2. Enzyme activity increases at higher pH levels, but productivity decreases due to reduced enzyme stability. For best operation, pH should be controlled as low as possible to minimize byproduct formation while maintaining maximum productivity. Presence of dissolved oxygen in dextrose feed is detrimental because of possible oxidation of isomerase cysteine residues, resulting in a loss in activity. De-aeration of feed to remove excess oxygen or addition of sulfur dioxide to reduce oxidation is helpful. Typically, 1 to 2 millimolar sulfur dioxide as sodium bisulfate is added for this purpose. Magnesium. The presence of magnesium is important as an enzyme cofactor for activation and stabilization of glucose isomerase enzyme. Generally, a magnesium level of 0.5 to 5 millimolar is recommended. Magnesium counteracts the adverse effect of excess calcium and commonly is added at a molar ratio of 20 times the level of calcium present. Cobalt and iron enhance glucose isomerase activity or stability, whereas copper, zinc, nickel, mercury and silver inhibit the enzyme activity. The next parameter is reaction time. Flow rate through a column is controlled to yield an effluent fructose level of 42 to 45% on dry basis. Under typical operating conditions, at a temperature of 60 degrees centigrade, an equilibrium fructose level of 51.2% is achievable. 48.6% fructose with a 95% dextrose feed. However, the very long reaction time needed to achieve the equilibrium level reduces overall productivity significantly. Control of all these parameters is required to achieve maximum productivity. If any of these conditions falls outside the recommended range, a temporary or permanent loss in performance can be expected. Temporary loss in productivity can be caused by a moderate change in pH, low temperature, high solids, insufficient magnesium or excess calcium. Correction of these parameters will reinstate column operation. More serious problems in productivity are caused by a temperature above 65 degrees centigrade or a pH considerably below or above the normal range. The one major disadvantage of column operation is that several months of potential enzyme use may be lost by an uncorrected fluctuation of pH or temperature to an unacceptable level. If reaction parameters are controlled within the limits recommended by the enzyme manufacturer, efficient operation over several months or longer can be expected. The enzyme normally is used through several half-lives until residual activity is reduced to 10 to 20% of the original level. The 42% fructose product containing 51 to 54% dextrose is refined by carbon and ion exchange treatments to eliminate color, off flavors, salts and other impurities and concentrated to 71% solids. A storage temperature of 27 degrees to 32 degrees centigrade is required to prevent dextrose crystallization. Products containing higher fructose levels are manufactured by a combination of chromatographic separation and blending. The refined 42% HFCS at about 50% weight by weight solids is then passed through a cationic absorbent containing calcium groups. The fructose is retained and a stream, that is raffinate, is collected containing predominantly non-fructose saccharides. The raffinate, composed of 80 to 90% of dextrose, 5 to 10% fructose and a higher saccharide fraction, is recycled to the saccharification or isomerization process. Elution of the high fructose fraction with water yields an high fructose corn syrup product containing 80 to 90% fructose and 7 to 19% dextrose. In actual practice, the separation process operates continuously in a simulated moving bed process, providing a continuous flow of enriched high fructose corn syrup and raffinate. The primary use of enriched fructose product is for blending with 42% high fructose corn syrup to produce a 55% fructose product containing about 40% dextrose. The 55% HFCS is evaporated to 77% solids for storage and shipment. Crystallization is generally not a problem due to the low dextrose level. However, a small amount of 80 to 90% HFCS is evaporated to 77 to 80% solids and sold as an non-crystallizable syrup. Crystalline fructose is manufactured using as raw material the 90+% fructose product obtained by chromatographic separation of 42% HFCS. The 90+% fructose material is evaporated to a solids level of 90% or higher, and the fructose is crystallized by batch or continuous techniques over a period of several hours or days. The crystalline product is washed free of impurities and dried. The most important property of high fructose corn syrup is sweetness. A 42% high fructose corn syrup product exhibits about the same sweetness as sucrose. 55% fructose is equivalent to medium sucrose invert, and 80 to 90% fructose is sweeter than sucrose. In general, HFCS exhibits the greatest sweetness perception under conditions of low temperature and low pH, and is less sweet at warm temperatures and neutral pH. Let us see the uses of high fructose corn syrup. The major use of high fructose corn syrup is in soft drinks. HFCS 42 is used in canning to provide sweetness, in dairy products as a bodying agent and to improve texture and mouthfeel, and in confections for sweetness, grain control and humectancy. HFCS 90 is used in reduced calorie products to lower caloric values by 30 to 50%. Continuous chromatographic separation technology allowed the production of two high value variants, that is HFCS 55 and HFCS 90, thus opening up large outlets for high fructose corn syrup, particularly in soft drink industry. To conclude this module, the development of second generation syrups with higher fructose levels greatly extended the use of HFCS in many applications. The technology for fructose enrichment is also used in a wide range of non-food applications. Syrups are used in perfumes to control evaporation, in air fresheners as humectants, to improve stability in adhesives, and as a setting retardant in concrete. Corn syrups are also used as carriers and for sweetness in medicinal products. Other uses are in dyes, inks, explosives, metal painting, shoe polish, leather tanning, and paper and textile industries.